Hi everybody, my name is William and today I'm going to talk about diffraction, its implication and its uses in ophthalmology. The aim of this topic is first to describe the phenomenon of diffraction, a wave-like property of light, and to further elaborate on the theory of diffraction and its knowledge extension in the form of airy disk and Rayleigh criterion, and also to explore the implication of diffraction from day-to-day basis. And I'm also going to give some brief examples of how our understanding of diffraction help us in real life, in particular the medical application of diffraction and some examples in ophthalmology. Diffraction is a phenomenon where a wavefront of a light encounters an aperture or the edge of any obstruction like side of a wall. It basically changes direction upon traversing the said aperture and the edge of the obstruction. It was first discovered and described by an Italian mathematician and physicist, Francesco Grimaldi, in the 1600s. And he coined the word diffraction from a Latin word of breaking to pieces. And to further understand the nature of diffraction, we need to first go through the Huygens-Fresnel principle, which states that for any unobstructed point on a propagating wavefront, it serves as the source of a new spherical secondary wavelet with the same frequency and the amplitude. It's important to realize that the amplitude of the optical field after the point of diffraction are composed of the superposition of the secondary wavelets as demonstrated by these diagrams here. Light comes through the aperture, diffraction occurs, and you have many secondary wavelets, and when these wavelets intersect, they are point of either superposition of constructive interference or destructive interference, and it's very well demonstrated in this second graph. This brings us to the notion of the airy disk. Now let's just imagine that we have a theoretically perfect optical system where there is no aberration. Light goes through a circular aperture and a circular diffraction pattern will be produced as a result. It was first described by the astronomer George Airy, and hence the name of airy disk, which describes this circular pattern of diffraction, which consists of a bright central disk surrounded by alternating dark and light rings as a result of constructive and destructive interference, as you can see here. Mathematically, the radius of the airy disk can be calculated by this formula, 1.22 times the focal length of the optical system times the wavelength of the light, and divide by the diameter of the aperture. So the radius of the airy disk is really proportional to the focal length of the optical system and the wavelength of the light going through the aperture, and it's inversely proportional to the diameter of the aperture. And as I have stated above, diffraction is very much aperture dependent, and the smaller the aperture relatively to the wavelength of the light, the greater the effect of diffraction. And one of the most important consequences of diffraction is that it places the absolute limit on the amount of detail in an image. And what does that mean? Now, the radius of the airy disk is has an important implication in ophthalmology. As you can see here, as described by Rayleigh's criterion, that two closely spaced airy disks are distinct if they are only far apart than the distance at which the principal maximum of one area disk coincides with the first minimum of the second area disk, as demonstrated by the graph below. When you have 2 point source and when the point maximum are beyond the distance of the Rayleigh criterion, the details can be resolved, and as these 2 points move close enough where one of the point maximum overlaps the minimum of the second Aries disk, this is what we call the Rayleigh criterion, and that's the minimum distance apart where 2 points can be resolved. And when you bring the 2 points closer, then the resultant point source will not be resolved. And this is important because in the average eye, the human eye, the exit pupil diameter is around 3 millimeters, and we have a focal distance of around 18.5 millimeters from the retina. Area disc radius is around 2 microns, or a diameter of 4 microns, which corresponds to the diameter of a photoreceptor. And no doubt that if we increase the aperture or the diameter of the pupil, we could potentially further decrease the amount of diffraction. But in the human eye, what happens is that by increasing the pupil size, we would introduce effects of aberration, which further degrades the image quality. In principle, it works very well, and in real life applications, if we can correct for the aberrations, the telescopes basically relies on this principle where it has got a very big aperture, and we can still form very sharp images because the effects of aberration is well controlled by the optical design. There are many real-life examples of how we apply the knowledge of diffraction in medicine. In 1952, Watson's, Wilkins, Crick, and Franklin made the famous discovery of the structures of DNA, and that relies on basically the principle of diffraction, and they used the technique of X-ray crystallography. Furthermore, there's many other uses of diffraction, or at least the principles of diffraction. For example, the diffraction enhanced imaging, which relies on synchrotron radiation, basically produce intense X-ray beams. Now, conventionally, X-ray has been used in medicine for many years, where we look at the difference in the radiation absorption by soft tissues and to form an image, and it's very good to look at bony structures and to diagnose other medical conditions, and such as pneumonia with X-rays or chest X-rays. Now, in contrast to the conventional X-ray imaging, which detects the absorption of X-ray in soft tissues, DEI, or diffraction enhanced imaging, relies the detection of phase shifts inside the soft tissue. And how does it work? Basically, to analyze any soft tissue matter, a silicon crystal is placed behind the sample, where a ray of X-ray first going through the sample, and as the X-ray pass through the sample, they refract and scatter in different amounts depending on the tissue composition of the sample, and these X-rays then hit that silicon crystal, which cause them to diffract, and because they diffract by different amount, the constructive interference formed by these diffraction patterns are then recorded by the image sensor as difference in intensity. And through mathematics and very smart computer algorithm, we are able to form detailed image of the sample, and as demonstrated here, this is a conventional X-ray compared to an DEI, where we are even potentially will be able to see tendons as well as bony structures, which is not really visible on conventional X-ray. Now, bring the knowledge of diffraction to ophthalmology. We have a perfect example of multifocal intraocular lens, which provides patient with near and distance focus. Basically, this is to combine an anterior spherical refractive surface with a multiple posterior diffractive surfaces in the forms of concentric rings of steps of diffractive optical components. So how does it work? Briefly, basically the multifocal intraocular lens form two images, one for long distance and one for near distance, onto the subject's retina. Obviously, the formed images are not as clear or bright as a monofocal or conventional intraocular lens, which are only good for either long distance or reading distance. But it highlights an important use of our knowledge of diffraction, how we could really exploit the nature of the property of the light to form two images, and also to rely on the constructive interference of light to reinforce the images. Although the use of multifocal lenses, intraocular lenses in ophthalmology is not as widespread as monofocal lenses for a couple of reasons, and for example, many patients still complain of diplopia as a result of the multifocal lenses. And as I have described previously, the diffraction enhanced imaging are also used in ophthalmology, because the eyeball itself is soft tissue and quite difficult to image by conventional X-rays or even CT. The DEI principle has been used to look at ocular tumors, as demonstrated by this Chinese paper, use X-ray diffraction enhanced imaging study for intraocular tumor in human being. And they looked at, I believe, retinoblastomas in eviscerated eyes and compared the histology pictures with an DEI image into conventional X-ray. And also the use of diffraction knowledge in OCT has been highlighted, that because we, as I have spoken before, that diffraction really limits the amount of image resolution due to Rayleigh's criterion. We currently, there has been studies where they use smart mathematics and algorithms where they could basically break through the diffraction limit of the lateral resolution in optical coherence tomography, which again would allow us to make breakthrough in terms of ocular imaging to detect disease process at earlier stages, such as in macular degeneration. And I thought that's just another good example of the use of diffraction in ophthalmology. Primary diffraction is an interesting property of light, and with the understanding of its physical nature, we could work out the diffraction limited visual resolution of the eye, which is around 4 microns, based on the area disc and Rayleigh criterion, and any other optical system like the telescope. With this knowledge, we are also able to, through science, to invent techniques to study structures of materials like crystals, minerals, and DNAs. And we also come up with novel approaches to image structures such as soft tissues, and directly in ophthalmology, ocular tumors through diffraction enhanced imaging. And by manipulating the mathematics behind diffraction, we are also able to improve the lateral resolution of OCT. The direct application of diffraction in therapeutic ophthalmology and has been evidenced by the invention of multifocal intraocular lenses. And this talk is just a brief overview of what diffraction is and how we have studied its physical nature and applied the physics behind diffraction to benefit us in medicine and in science. And these are my reference, and thank you very much for your time.